Greetings and welcome, friends. Today we're talking about solving systems of 3 equations and thereby 3 unknowns. So we are currently masters of solving systems of 2 by, right? Maybe you knew how to solve by graphing, just finding the intersection of 2 lines. You could solve by substitution. You could solve by elimination method. Today we're going to talk about something a little bit more complicated. Now think about a one-dimensional, right, line sort of thing. If I was talking about a point on a line, it'd look something like that, right? It wouldn't be very interesting. Two-dimensionally speaking, right, when we talked about a system and the solution, right, two-dimensionally we had a system of 2 lines, something like this and this, and we found their intersection, right, and that was a two-dimensional point like an x comma y, right? It turns out that 3-dimensionally speaking, let's see how well I can draw, and then imagine like I have an axis coming out at us and then going away from us this way. Oh, craziness. All right, so imagine 3 directions. Crazy stuff, I know. And instead of lines, an equation in 3 variables actually is going to represent a plane. All right, which a plane is a 2-dimensional surface that heads out in all of its directions infinitely. All right, so imagine like an entire plane. So you could think of the floor of the room we're in if it was to travel out beyond our walls in all directions infinitely. That would be a plane. All right, so if I have a plane there, and then let's say I had another plane. Let's see how well I can draw this. All right, here 2 planes could intersect, and what's the intersection of 2 planes going to be? I don't know if you could tell. It would be a line, or 2 planes could intersect at a line. They could also be parallel. Okay? Now imagine 3 planes intersecting. All right, I'm going to try to draw this as best as I can. Yeah, you don't worry. No, just follow along if you can't draw it. That's fine. So 3 planes intersecting.
Why are they 3 planes?
They're not cars.
All right.
I know.
So 3 planes intersecting, you could imagine them crossing and having a single point in common. All right. So the way to simplify this, imagine a box. All right. Well, because I was just trying to show how it might look in that way. So here's plane 1, here's plane 2, here's plane 3.
Oh, like,
and they intersect at a corner. PLA and E, I guess that still is the same spelling. But yes, a plane is just like a line is infinitely long in 2 dimensions. A plane is infinitely large in 3 dimensions, but flat. So right, imagine like 2 walls in the ceiling intersecting to form the corner, right, of the room or something like that. So they would have a point of intersection, 1 point in common, and that wouldn't be an ordered pair. What do you think it would be called? An ordered...
the 3 Musketeers.
Ordered triple. Right? So this is an ordered pair. This is referred to as an ordered triple. Okay? So this is a drawing of a unique solution. All right? So it's possible to have a unique solution occurring where there's just one, right? So this is unique. There we go. It's also possible to have infinitely many solutions. All right, which infinitely many solutions would be something more like, there's actually multiple ways it could occur, I suppose. But imagine I have 3 planes that are all the same plane. That would work. Let's see. Imagine that three planes happen to coincide in such a way, like an X, but then the third plane also crosses at the same point on the X.
Have you guys wrote anything down yet?
Don't worry, it's fine, it's fine. So it's possible to have three planes form in like an asterisk shape that's been extruded in 3 dimensions, where they would have infinitely many points on a line. Okay, so infinitely many solutions that form a single line. Shh, ladies, gentlemen, please. Right, that's one possibility for infinitely many solutions. Or you could have, right, 3 planes that just coincide, and then there's even more infinitely many solutions if you wanted to think about it that way. Technically, it's the same infinity. But and then there's also a possibility for no solution. Okay, so that could occur if you have the following. You could have 3 parallel planes. All right, so that could happen. You could also have, imagine, let me see if I could draw this picture. I'll just draw a little sample like this. Imagine a triangular prism, like a little tent. All right. Now, so I've got plane 1 here, all right, this outside of the tent. It intersects with the bottom plane, right? But those form a line together. However, the points on this line have nothing in common with the points of this wall of the tent, the back wall, right? Because, sure, these two have some in common, these two have some in common, those two have some in common, but there are no points that are common to all 3. All right, so that's another possibility is some point, so this is like some points are occurring between 2 of the planes, but not all 3 of the planes. All right, so you could have something weird like that. So there's actually a variety of different ways that you could have no solution. So anyways, so that's what some weird possible outcomes are. But we're hopefully going to be finding the ones where we find the one point, the corner point, so to speak, where we have an ordered triple, a unique value of x, y, and z that will make all 3 of our equations true. Now don't worry, we're not going to solve any of these graphically. We're going to solve them algebraically, and maybe that is a reason to worry, perhaps. So let's do an example. Exemple. Solve the following. Let's say I've got, actually tell you what, I can even just take a snapshot right over here. I'm going to just do that, bam, for my little lesson plan here. So that way I minimize possible misinterpretation there. So here's a system of 3 equations and 3 unknowns. All right, so if I'm looking for 3 unique facts, I need, right, 3 equations to help me find those things. I need 3 clues to help me find the 3 culprits here, sort of thing. Right, so I've got a series of facts. I know that x minus 2y plus z equals 15. I know if I have twice the value of x plus 3y minus 3z, that's equal to 1. Right, and I've got all sorts of different facts that I have together here. Now, we are masters at solving systems of 2. So if I could somehow reduce this, all right, to a system of 2, then I'd be good, right? If I could get rid of one of the variables twice, then I'd be left with 2 equations and 2 unknowns. All right, so that's what our general goal is going to be. So we're going to try to reduce this to a previously solved problem.
Step 1.
No, this is just in general what we're doing. And we actually can use either elimination or substitution. For this one, we'll do substitution. The next one, we'll do elimination. So I'm going to try to eliminate the same variable twice. And I'll just make that like my bullet that will do that for us. The same variable twice. This is the easiest way to do it. I mean, I could do all sorts of crazy manipulations to this, but this will be the simplest. So let's try by substitution in this case. So if I'm solving by substitution, of the 9 choices I have, which variable and which equation would you like to solve for? Which x? There's 3 of them.
I'd say the second one down,
Why would you choose that one?
because,
First one.
no, I would say it because,
No.
I would say it because, it equals the last number.
No.
Right, but by solving for that x, I'd have to divide by 2, creating a bunch of fractions.
That first
Okay,
one
say
has
the
no
top
coefficient in
then.
front of it.
So I would recommend solving for either the first equation's x or the first equation's z if I wanted to avoid fractions. Jacob, it still could be done with all those fractions. You would just brute force your way through a lot of fractions in doing so. So let's do that. So x minus 2y plus z equals 15. So to solve this, I'm going to add 2y to both sides, subtract z from both sides.
Because it doesn't have numbers in it?
Yeah, it's got a positive 1 coefficient, or a negative 1 would have been equally easy. So, so I'll get x is equal to 2y minus z. I'll try to have my z's with a little cross so my 2's don't get mixed up with them, plus 15. And this would be my revised equation. Right? And now, if this is truly equal to x, that means I could replace any x at any time, right? And that's fine. That's a legal thing to do by substitution. Now what we're going to do, I want to eliminate the same variable twice. Notice x is defined now all in terms of y's and z's. So if I replace the second equation's x with y's and z's, some expression of y's and z's, there would be no more x's in this equation, right? Correct. And if I replaced the third equation, x, with something that's all in terms of y's and z's, there would be no more x's in that equation. So notice I would actually eliminate the x's in 2 of these equations, right? I'm eliminating the same variable twice, and I'll have 2 equations all in terms of y's and z's. And if I have 2 equations and 2 unknowns, I call that a system of 2, which is a previously solved problem. Well, that's what we just had, right? We've got 3 equations and 3 unknowns, Jacob. Yes. So let's do this substitution. So 2 times, and instead of x, I'm writing 2y minus z plus 15 plus 3y minus 3z equals 1, right? So the whole x got replaced by this expression. Use parentheses, right? Indiana Jones put his sand in a bag. He didn't just throw his sand at a pedestal. That wouldn't have been helpful. So for parentheses, and instead of x, I'm writing 2y minus z plus 15 plus 10y minus 5z equals negative 3. Yes, bless you. So I've double substituted. And notice this is now perceived as a new system of just 2 variables. I've got a lot of simplifying to do, but we're almost there. So let's do that. So let's see. I'll simplify this top one here. And so I'm going to be going from here. That's fine. So I'll have 4y minus 2z plus 30 plus 3y minus 3z equals 1. I'm going from here to here.
So,
I distributed the 2.
distributing, so you have to do the
Yep. And now I'll combine like terms on it. So let's see, how many y's do I got? How many z's do I got? And maybe I'll even subtract the 30 from both sides while I'm at it. Right. Yeah, I'll try to make it look like those guys are friends there. So, how many y's do I have? 7y. And I've got how many z's? No? Negative 2, negative 3 becomes more negative. So negative 5z. And 1 minus 30 is negative 29. Right? And let's get the other equation in here too. Right, so yeah, that's the unfortunate thing. My work is all intermingled here.
This is like a messy problem.
Yeah, sadly. For substitution, we'll find a way to, or sorry, for elimination, I'll have a way of labeling this a little bit more nicely. So this is, let's see, 4 times 2y is 8y minus 4z plus 4 times 15 is 60 plus 10y minus 5z equals -3. Combine like terms there and move the constant to the other side, right? So 8y and 10y are friends, -4z, -5z, and we'll move that 60 to the other side. Why not, shall we? Why not, shall we? So how many y's do we got? 18y minus 9z equals -63. So between this equation and this equation, I now have reduced the problem to one that's previously been solved by us. Not identical to this, but this concept, we know how to solve systems of two. Let me just rewrite this one down here real quick. Actually, what's up?
So all that work we just did to do what we did last night for homework,
Right, to bring it down to something that was like a problem for last night's homework, yeah.
that is pretty gross.
So, for this system of two, I could now continue to choose substitution again, but I think elimination sounds nice. I don't know about you guys. Let's see, 18 and 7, what do both of those go into? Well, I think they're relatively prime. 7 times 8 is what? Man, my mind just went blank. 56 plus 7 times 10 is 70. What's that, 136? Yeah, that doesn't sound helpful. 9 and 5, 45, right? Okay. So, what do I multiply the top equation to get a 45? 5, yep. And what do I multiply the bottom equation to get 45? 9, and why not make it negative just to get those opposites that we're looking for, right? And you guys know how to go from here, right? Right? Good stuff. So let's see, 5 times 18, 50 plus 40 is 90y minus 45z equals, let's see, 5 times 63, 15 plus, what's that, 300, negative 315. Did I do that right? I believe so. See, negative 9 times 7y, what's that, negative 63y? Negative 9 times negative 5 is plus 45z. Equals, and negative 9 times negative 29, well, it's positive, I'll tell you that much.
Wait, what is it?
9 times 29 is the same as 9 times 30 minus 1. Do you agree? So that's 270 minus 9, or 261.
Yep.
Right, do you guys agree? You like that? Like that little trick using distributive property to help me do the math? I like it. It's a good little trick. And hey guys, look it, we got our opposite z's. Hooray! So let's add them up. 90 minus 63 is going to be 27 y's. The z's cancel out. And 315 and 261. It's going to be negative 54 by the looks of things. And how do I solve that for y? Hey, guys, I'm down to one equation and one variable. We know how to solve that. It's like a system of one. Yeah, aren't you excited? We just... y equals negative 2.
So we only solve the
Right. Okay, good call, good call. So, yep, accurate. We'll probably use a full sheet on this problem. That's fine. So guys, this is solved for y. Where should I plug this? Look at all this.
The first one.
The first one,
There's three.
Actually, one of them.
well, it'd be better for us to plug it into one of these guys.
Yeah.
And why is that better? Because there's only two variables in either of those equations. So if I replace y, I know I'll be able to find z. Okay? So I'll plug it into the second one of those, I guess. So I'll have, let's see, 7 times negative 2 minus 5z equals negative 29. Right, so that's negative 14 minus 5z equals negative 29. So now I can solve this for z, right? Add 14 to both sides. So negative 5z is equal to, I'm adding 14, negative 15. So z is equal to 3. Oh man, I'm at the bottom of my page. So now I know both y and z. I want to find x.
Oh, wow.
What should I do?
I'm done.
I'm going to take both y and z and plug it into where? What's a good place? How about this right here? This looks pretty good. That'll solve for x, my very first revised equation. This is where multiple colors can be helpful. So 2y minus z plus 15. I'll do that down here. So x equals 2 times y was negative 2 minus z is, so minus 3. Was that plus 15? Thank you, thank you. And now I can just evaluate this. So that's negative 4 minus 3 plus 15, negative 7 plus 15, x equals 8. So our ordered triple, what order do you think we should write this in? Alphabetic order, that's right, x, y, z. So 8, negative 2, and 3 would be the one single point that works in all three of those equations simultaneously.
Let's never do that again.
Let's do that again. Good request.
I said never.
Let's never not do this again. Good request. Let's take a look at another problem here.
Yeah, I don't need it. We don't need it.
Oh, we do need it though. It's a different method. So here we go. Here we go, friendly friends. Don't you worry. Paste. So guys, here's our last example we're doing today. Shh, ladies, gentlemen, please. So solve 5x minus 2y plus z equals 11. 2x plus y plus 3z is equal to 0, or 6x minus 2y minus 2z equals 16. So system of 3. Now this one we're going to use the elimination method, but our goal is the same. We're going to try to eliminate the same variable twice.
Wait, you have to wait for us to break.
Yep, I'm aware of this, yep. I'm aware. Good point, good point. So instead of just finding opposite x's, I'm going to want all three x's to be opposite. But wait a minute, I can't have three things be the opposite of one another. So two of them will be the same and one of them will be the opposite. All right, does that make sense? So friendly friends, between 5, 2, and 6, what would their quote-unquote LCD number be?
It's gotta be, I would say 30.
I think 30 is right. Between 2, 1, and 2,
2.
that one's looking pretty good right there. And between 1, 3, and negative 2,
It'd be 3, or no, 6.
6. I believed your 3 there.
Yeah,
It was
I wasn't
persuasive.
thinking it was- yeah, I know.
Very convincing. So guys, for the 2's, we're going to choose the y's. I think you guys would agree. And notice 2 of them are already negative. So I just want the second one to be positive, so when I can combine it with the other 2, it'll eliminate them. All right, so I'll try to make this a positive value. Now, one of the things that will be helpful to us is by labeling our equations. So I'm going to label the first one A, the second one B, the third one C. All right, this is going to help us organize our stuff because as you saw with the previous problem, there's a lot of moving parts there. It'd be very easy for us to get confused. So how am I going to get opposite y's? What equation am I multiplying by what? Or am I multiplying multiple equations by things? I want to multiply equation B by what number? 2. So I'm just going to say this is what this line represents. It's 2 times B. So let's see, what is 2 times B? 2 times 2x is 4x. 2 times y is plus 2y. And 2 times 3z is 6z. And don't forget to multiply the right-hand side, although in this case, 2 times 0 is still 0. So I am now going to do what? If I add this new equation to C and A, I will eliminate the y twice. And I'll have 2 brand new equations, all right, which will only have 2 unknowns left over because the y's will be gone. They'll both be in terms of x's and z's, which is good news for us. So let's see, just to describe my work, I'm going to do here A plus 2B, right? And then I'll do C plus 2B, right? So labeling my work just so I don't get lost along the way. So let's see, A plus 2B. So I'm combining this guy and this guy, right? You're welcome to rewrite lines next to each other for the adding part so you don't get confused because I know sometimes jumping lines can be confusing. But for the sake of not having to write it over and over again, I'm not going to do that. And neither do you have to. You don't have to, right? So 5x and 4x is 9x. Negative 2y and positive 2y is 0. Hooray, we eliminated it. And 6z and 1z is 1z. 7z total. And 11 and 0 is 11s. Right? Ooh, this is looking good. I've only got 2 variables in that equation. Now let's do C plus 2b. So 6x plus 4x is 10x. Negative 2y and positive 2y is nothing. And negative 2z and positive 6z is a 4z. And where am I here? And that's why it's nice because see I just got lost for a second. C plus 2b. So I'm doing 16 plus 0 is 16. And I'm going to actually, because this is a crazy name for this and this is a crazy name for that, at this point, now that I've gotten it down to a system of 2, let's relabel these. Let's just call this equation D, this equation E.
Shouldn't that 16 be a 32?
No. Because the 16 came from the plain old C
Oh, yeah, okay.
plus the 2B row. Yep. So 16 and 0 was 16. So I'm going to call this D and E just so I don't have to use all these crazy, right, longer names for them. So, okay, we could do substitution if that made sense, but all of these, as you can see, have coefficients. Let's do elimination. I like elimination a lot of the time, too. So between 9 and 10, what would their LCD be?
90.
90. Between 7 and 4?
28.
28. So what's my next row of work going to be? What would I multiply line D by to get a 28?
4.
4. So I'm going to have 4 times D. And what would I multiply line E by to get a 28? Negative 7. I like the negative because it'll give me the opposite that I need, right? Since both of those started with the same sign. Right, so as long as I'm kind of labeling my work, I won't get too lost. So let's do this. So 4 times D, 4 times 9, 36x. 4 times 7 is plus 28z. 4 times 11 is 44. Don't forget to multiply the right-hand sides. And now negative 7 times row. Oh, I just labeled this wrong, guys. Oh, classic. Fortunately,
Smurfing kidding me?
no kidding. Negative 7 times 10, negative 70x. Yep. Negative 7 times 4, it's negative 28z. And negative 7 times 16, let's see, 7 times 6 was that 42, plus 7 times 10 is 70. What's that? I already forgot. 112. And is it positive or negative? Negative. Right. So now, what do I do now, guys? We don't. That's my perfect point. We've got a lot of stuff going on. It's like, all right, I just did a lot of math. I don't know what it got me.
Okay, we make a new equation called F.
We don't have to necessarily. Well, what was the goal of all this? I just got opposite z's, and now I'm going to add them up. So let's see, 36 and negative 70, what's that going to be? Negative 34, is it? All right, thank you. And 44 and 112 is going to be negative 68. Guys, we've got one equation and one variable.
X equals 2.
How'd you do that? Black magic?
Are you okay?
Wow. No, we divided both sides by negative 34. We don't have to label anything. Could I have called this equation f? Sure. Could I say multiply both sides of equation f by, right, 1 negative 34th if you wanted, but no, that doesn't. We don't need to do that anymore. Our labels are no longer helpful. X equals 2. All right. So I found one of my solutions. What should I do? Where's a good place for it? Why would I not plug it into A, B, or C? Because I would still have 2 unknown variables, which I could do and then solve another system of 2, but that's not as easy as...
You put it into...
Which do you like, D or E? D or E?
E.
All right, I'm hearing E.
No,
I
D.
like
D has smaller numbers.
Yeah, I want 7
It doesn't matter. You guys can branch off from here if you really want to. So 10 times, instead of x is 2, plus 4z Willow equals 16. So 20 plus 4z is equal to 16. Subtract 20 from both sides. Oh, guys, we're cruising right along now. We're going to find this solution to this system of 3. Sorry, we're finding z. It's like I'm on a mission here. This is amazing. Let's see, divide by 4. 4z equals negative 1. I'm able to write really fast on my little tablet here, that's all. I write a smaller overall distance than you do. I don't have to move my hand to write. So, I've got x, I've got z. What do I do?
You have to put z into the first revised equation, which would be, I would put it in.
I would go for the middle one.
Why do you like the middle one, Kirsten?
There's a 0 and there's the little numbers in it.
And what variable am I looking for?
Little y.
I'm looking for y. I like this one for all of the reasons you said, right? There's small numbers, there's a 0, but also look at y has no coefficient other than the positive 1. So that one sounds really good to me. So let's take, and I'm going to draw my arrows here. This one and this one are now merging.
Oh yeah, got that.
And plugging it into equation B. Bop, 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 bop. So let's see. So that's 2x plus y equals 2x plus y plus 3z. So 2x plus 3 or plus y, sorry, plus 3z equals 0. Right? So I've replaced both the x and the z, leaving me with one equation with one variable. How great. 4 plus y minus 3 equals 0. I could combine those, I guess, if you want to think about it that way. I don't know. It's all up to your own preference from here. What's that? Y plus 1 equals 0. Oh yeah, we'll subtract 1.
Okay, so now we have to write them, algebra, how about that?
Right, as an ordered triple. So 2, -1, -1 is our solution. So yep, you guys probably agree that these problems are quite long, but the general theme is boil it down to a system of 2, right? If I can rewrite it as something that I know how to solve, then I can walk the rest of the way using my previous skills, which I know I'm good at. So do that by substituting for the same variable twice or eliminating the same variable twice. Thanks for watching, internet friends. Bye-bye.
Mine